Hi.
Hi, Simone.
Jackie, you're going through the slides, right? You're presenting the slides, or do we share it?
Yeah, I'll share my screen and then I'll just pull up each person's talk just to try to keep it a little bit more streamlined. It's stressing me out, but I'll do the best I can. It'll be fine. I tested all the talks. Everybody's talks look great. So yeah.
You'll do great.
Don't stress it too much.
No, it should be fun.
Okay, I'm going to go ahead and get started with a brief introduction. I know that we'll have more people filtering in. My name is Jackie Schumann. This is the Fire Cross Working Group session. And so, oh, jeez. There we go. It's good that I figured this out now. So we'll have 6 talks, 5 minutes each, followed by 2 minutes for questions. And then we have 2 posters that will give a little preview talk. And then we will have a discussion at the end. And so, oh my gosh, this is going to drive me crazy. Okay. So we've had historic fires globally. I just want to put us back into context. Depending on where you're coming from, atmosphere, land, surface, you think about a different thing when you think about fires. We had the Australian Black Summer. We had South African library, giant fires within the wildland urban interface. We've had a method for recent detection of zombie fires in boreal Alaska, but they're also detected in Siberia. These are fires that overwinter, and then once the fuel is dry enough, they reemerge with burning. But there was a recent paper about how to detect this from remote sensing, and it seems to be, it's been around for a while, but it's a larger problem than previously was thought. And then here in the United States, drier fuels are connected to larger fires. And so the figure on the left is a study that was published in 2016. And for the recent period, 2000 to 2015, you can see the fuels are drier and they have a much larger burned area. But if you were to do this research again, the trend continues. Within California, here in Colorado, we've been breaking records in terms of area burned. And then just because you don't have a fire occurring where you are locally, you still experience those events. This is a picture I took from my backyard, and this was probably a local fire, Colorado fire, but we have fires from, California that travel here to Colorado. The Australian smoke traveled much further than Australia. So it's it's a big issue that we need to think about on a lot of scales. But in good news, governments are taking action. Joe Biden just released his 2022 budget, and it makes significant investments to wildfire risk and to address wildfire risk and climate change. $80 million to mitigation, $20 million to rehabilitation of lands, and then $5 million to the Joint Fire Science Program to look at how we can tackle this, the climate change impact specifically. And I put this up here to show that people are taking interest. There are things that we can do. And so it's a positive step forward. And so with that, I'm going to switch over to our first talk, which will be Dave Lawrence. Take it away, Dave.
Okay, great. So I'm actually going to present on behalf of Fong Li, who is the primary author of the fire code that exists in CLM5, and she gave me most of these slides to present. And so, you know, as always, there's lots of people who are involved in this project, but I've been the main facilitator over the last few years of helping Fong get the fire code into CLM. Although we have also worked with the chemistry group for fire emissions. Next slide. So this is how the fire works. It's kind of complicated, and I'm going to try to go through this slide in CLM5 and CSM2. So there are 4 types of fires that can occur in the model, and so that's the red sort of set of boxes midway down the slide. So there's agricultural fires that can only exist on cropland. There's what she calls non-peat fires, which is basically natural fires or human ignited fires that occur in naturally vegetated parts of the world. There are deforestation fires, which are fires that where, especially in the tropics, where closed tropical forests, where people are using fire to do deforestation, and then there can be fire that sort of moves beyond the area of the deforestation. So they call escape fires. And then there's also peat fires in places like Indonesia, where those can have big emissions as well. So, and each one of these fires has a different kind of way it's ignited and controlled. If you look at crop fires, that sort of the timing of what's going on with the crop cycle. So where people are maybe clearing land, you know, to before they do planting. It's dependent on socioeconomic factors like GDP and the population density will affect agricultural fires. In the natural fires region, fires are ignited by lightning or humans, and then suppressed by humans, and that's controlled again by population density or GDP. Whether or not a fire can get ignited, there needs to be vegetation there, and then also the weather and climate conditions need to be suitable. And in CLM5, that's it's the air humidity and the soil moisture, which are the triggers. The deforestation fires are triggered by a land use change event in the model, and then peat fires are triggered by weather and climate conditions that are suitable for peat fires. So once a fire has occurred, then you calculate the area of the fire, and I'll talk about it very briefly. Once you know the area, then you can calculate the carbon consequences and the fire carbon emissions from that area that has been burned based on the vegetation carbon distributions in that grid cell. There are emissions factors associated with each plant functional type that will then also determine other trace gases that get emitted when there are fires occurred. And there's also a fire emission height associated with each plant functional type that differs, so to find out the injection height. So next slide. So if you to determine fire occurrence, you use this equation here. So at every time step, you would calculate this and find out the number of fire counts within a grid cell, which is based on the ignition counts, which is Ni, which is lightning plus human ignitions. We take lightning from offline database climatology. Fuel availability, there needs to be carbon there to burn. Fuel combustibility, that's the climate factor. And then there's this non-suppression rate. So the extent that humans are not suppressing fire, so that number would be 1 if there's no suppression, 0 if there's strong suppression, And that tends to have this sort of distribution where it peaks, sort of there's very little suppression at very low densities. It comes up at higher population densities and then comes to very low fire occurrence at high densities when GDP is high enough that people can stop fire. And then the climate consequences here, or climate factors, FM, relative humidity and soil wetness, both have these curves that determine the likelihood that an ignition will occur. Next slide. Once you've had a fire that has been initiated in a grid cell, then you need to calculate the area. And I won't go through the details. In basically the UP there is the key value in the middle of the slide there, which is the fuel wetness times the wind speed. And those are the two factors which will control or determine how much the fire was spread. And the average then area that you calculate from that is then down-regulated by some suppression efforts by population or GDP. Next slide. I won't go into this one in the interest of time, but there's different controlling factors for agricultural fires, deforestation, degradation fires, and peat fires. Next slide. And so just, how well does the model do? I realize I'm at 5 minutes. Comparison to GFED, GFED4 or GFED Forest, which includes more small fires, it's in the right ballpark. This is CLM4-5. CLM5 is even a little bit better. And CSM2 is roughly equivalent to CLM5. So compared to other global fire models, I think the CLM5 fire model is comparing okay. You can certainly find deficiencies. And if you, went into a specific region, I'm co-authoring a paper right now that's looking at the Western US, and we're overestimating fire in the Western US by almost a factor of 2. But globally, the map looks about right. Next slide. And this is just, I'm not going to go through this, some of the things that Fong is thinking about working on if we were going to continue to develop this fire model further. And I think we'll see a few more results in a few of the next presentations about the performance of the fire model in CSM2. Stop there.
Thanks, Dave. Will, is there time for questions?
Yeah, Dave, you've got a minute left, and Alan Roebuck had a question in the chat asking why lightning's not part of weather and climate.
Yeah, so
why are you reading it in?
Yeah, it's CAM. My understanding is that CAM can calculate lightning, although it's not a regular part of a CAM calculation. And so currently we're prescribing from an offline file, but that was one of our discussion topics later. It would be a nice way to connect CAM more to CLM is if we actually took the prognostic lightning from CAM to the extent that they can do that. So that is a hopeful future endeavor, no matter which way we go in terms of developing the fire model.
Thanks. If you have other questions for Dave, go ahead and put them in the chat, but otherwise, Jackie, we should probably move on.
Okay, thank you. So I'll be talking about additional opportunities for fire research when we include dynamic fuels and size-structured vegetation. And so the additional component that CLM5 does not capture is dynamic fuels and vegetation. And so to address this, we've adapted the Spitfire model into FATES. So FATES is the functionally assembled terrestrial ecosystem simulator. It's a module that runs within CTSM. It replaces the traditional big leaf vegetation shown on the top left with more realistic size structured vegetation. So by doing this, we can capture dynamic vegetation, competition, ecosystem assembly, and vegetation distribution through time. On a heterogeneity, we can have grid cell heterogeneity with different patches. And so Spitfire uses the same Rothermel fire behavior equations that Fong uses, and it brings in the ignition data set as well as weather. The fire weather is evaluated in conjunction with the fuel state and how much of that fuel will combust. From that, we calculate fire behavior, total area, intensity, and duration. For a specific fire, you then evaluate vegetation mortality based on cambial damage, so damage to the bark, as well as crown scorch, damage to the foliage. With that damage, you get subsequent vegetation regrowth, and then you start the cycle again. And so fire is evaluated daily for each patch on a grid cell, and the patches retain the surviving vegetation for the next time step. And so what can we do now? We're getting much better at capturing biogeography as driven by the interaction between fire, climate, and vegetation traits. And so for across South America, for the fire regime shown on the left, we get a distribution of a thin bark tree in the areas of low disturbance shown as white, whereas we have a thick barked fire tolerant tree in areas of intermediate disturbance, and then grasses in the high disturbance areas. And this distribution of the thin bark versus the thick bark tree broadly corresponds to observations with thin barked trees shown as blue in the figure on the right. The mechanism of mortality shows that small trees of both types are vulnerable to fire, as seen by the dark fire mortality colors, but as the thick bark tree grows in size and accumulates more bark, it escapes fire mortality. We also have collaborators at Los Alamos are leading an effort incorporating live fuel moisture. Live fuels are very dynamic through time, much more dynamic than dead fuels, which change very slowly. Using Fates Hydro, we can capture water content at sub-daily scales and look at changes in live fuel moisture. And so the figure on the right shows the increasing number of days with live fuel below a critical 79% threshold. And that number of days and subsequent fire risk is increasing as you move out into the future for an RCP 4.5 scenario. Active crown fire, where we have a procedure implemented where you can track the vertical propagation of fire through the crown, depending on the fire intensity and the crown fuel density and moisture. We're looking at topography and hydrology interactions using the CTSM hill slope hydrology remapping. And so do heterogeneous hill slopes and their different water tables carry on to fire behavior. Management and mitigation. Fires within the wildland-urban interface are increasingly problematic. And so fuel managements are inherently size structured. And so using the Fates logging module, colleagues at Lawrence Berkeley are going to be looking at whether or not we can capture changes in fire behavior based on prescribed management treatments. And then also degradation associated with fires. Degradation, shown at the top is a figure for the Amazon with areas of deforestation highlighted in red. And so for this particular region, deforestation is more than 40% of all the fires. This type of degradation increases forest edges, so you get small patches of forest. And larger edges are associated with increased heat percolation and then increased fires. And so the figure on the bottom is a long-term burning experiment. And so you can see different disturbed canopies. These disturbed canopies have less humidity inside the canopy and drier fuels on the ground, making them more susceptible to fires. We're integrating land-covered land use change data sets into Fates, but including this type of degradation is an important feedback onto fire behavior. And so with that, I just want to highlight Fates Spitfire as a tool for action. And so we need to consider the consequences of our choices in terms of management. And so this is a decision framework put out for stakeholders and managers of systems. But a lot of these choices have to do with the connection between fire and fuels, and the size, structure, and type of vegetation are really important for that connection. And with that, I'll stop, and I look forward to our discussion.
Great. We've got about a minute for a question. Jackie, I'll get one for people who aren't super familiar with the differences between the Spitfire approach and Fang's approach. Can you kind of summarize what the key, like what's the important take-home difference between how FATES handles fire and how Big Lake CLM handles fire?
So the fundamental fire behavior equations are actually the same. They both use a Rothermel approach, which is a traditional Rothermel-Van Wagner equations of fire behavior. And so it has to do with, empirically derived equations of how the fire acts in terms of fuel moisture and subsequent fire area and behavior. But FONG has a lot more functionality in terms of deforestation, peat fires. And so it's the fundamental difference between them is that the fuels in the big leaf fire model are not dynamic. And so the gains with something like FATES would be the ability to look at this dynamic change through time.
Great, thanks. We should probably move on.
All right, great, thanks. So this is a quick summary of two studies that I've been involved with over the past year that have really changed the way that I look at wildfire as an interactive component of the climate system. So rather than just a passive kind of responder to the climate, this suggests that wildfires are really an essential part of the component, the coupled climate system. And the picture that you see here is a good example of that. So this is the Australian wildfires from early January in 2020. The red dots are the individual fires, and you see the emissions over the continent being advected over the southern oceans and starting to interact with the cloud fields. And I think this is a good picture to emphasize the cross-working group aspect of this discussion, because those are advected over the southern ocean. They interact with clouds on a microphysical level. They have direct radiative effects as well. And then, as I'll show, they actually have a response in the ocean. And so you're tying together the atmosphere, the land surface, and the ocean with this kind of one topic of case study. Go ahead and skip. So some of the background, wildfires, if you look through the literature, the wildfires have traditionally been viewed as kind of this passive component that's responding to the climate system. And really what we see now in CESM2 is that they play an active role in driving climate responses. And this speaks to the whole manner in which wildfires are prescribed, for example, in the CMIP configurations. And so we really need to rethink. In recent decades, part of this is the fact that wildfires have become larger and more intense. So you have these larger emission events, and that's part of it. But the other part of it is the fact that the clouds in the climate models have also changed and become more interactive on a microphysical level with the biomass aerosols. And so we've really seen this kind of step change in their effects within CESM. And so the basic motivating question here is, what are the climate responses to recent major wildfire events in CESM2? And what does that suggest about how we actually go about representing fire in climate predictions and also climate projections? And I'm arguing here that fire is both an important feedback within the climate system, but also a source of predictability. And these two case studies kind of illustrate that. Go ahead, next slide. So the first case is something that was discussed briefly yesterday morning. Perhaps you saw it. It speaks to how the CMIP6 biomass emissions are prescribed. And so there was a decision made when putting together the emissions data sets that the variability in the satellite era, as you see in the red, kind of on the right-hand side of that graph, would be preserved. And so you have this large variability that's spliced onto a record with almost none. And so there's the step change, kind of spurious transition in variability. And the question we had is, what's the climate effect of that step change? And so in the red, you have the CMIP6 projections, and that applies to the time series on the right as well. And then in the black, we've homogenized these emissions where we've just prescribed a mean annual cycle. And this is just from 40 to 70 north. And what we find is that there's a large climate response, just this narrow band of emissions and the variability in that band. So we have 20 ensemble members in the black and 11 in the red. And what you see is that north of around 30 degrees north, you have this spurious warming that is driven by this spurious transition of variability. And it's not small. It's about half a degree C over much of the northern hemisphere. And at its core, it's driven by the fact that the large variability in the emissions is thinning the cloud field. And so that's allowing more shortwave radiation to be absorbed by the system, both at the top of the atmosphere and at the surface. And in turn, that's probably triggering a number of feedbacks in the cryosphere with snow melt at the surface and sea ice. And so interestingly, even though we have the same net amount of emissions, the structure of those emissions and associated nonlinearity seem to be driving this robust climate response. And it's not a small effect, as I say. If you look at the difference between CESM1 in the blue and CESM2 in the black, the majority of that difference and in the CMIP6 forcings in the red is explainable by the actual biomass emissions. Otherwise, they look like very much the same model. So it's not about climate sensitivity. It's really about the forcings and what they're doing within the model. If you want more details on this, by the way, I have a poster later in the poster section, and I can go into the nitty gritty. Next slide, please. And so the second case is trying to simulate the climate response to this 2019-2020 Australian bushfire season. And what we've done is we've actually prescribed the emissions in the model and looked at the coupled climate response using 50 ensemble members. What's interesting about this is in many ways it mimics the climate response to a large volcanic eruption.
John?
Yeah.
Oh, you can keep going, it's just eating into question time.
Okay, I'll make it quick. So the effects of these aerosols in the clear sky is actually quite small. So it's about 0.2 watts per meter squared. But when you look at the all sky effects, they're actually very large, around 2 watts per meter squared, and that's on par with volcanic eruption. And the reason is because the aerosols are brightening the cloud fields, and they're doing so across the southern hemisphere. So it gives you this large interhemispheric energy imbalance. And in turn, the model simulates a disposition towards La Nina in 2021, which is actually what we saw. And like I say, if you'd like more information, see the poster session. And then you can just skip to the next slide for summary points, and I'll take any questions.
Great. We've got about a minute left. If anyone has a question for John, you can drop it in the chat or raise your hand.
I have a question. John, do we have a sense yet about whether there's something particular about fires from Australia that would make it more sensitive than fires from elsewhere, that going over the Pacific, aerosols going over the Pacific where El Nino can control sea surface temperatures or something like that?
Right. Yeah, I think the latitude is a key part of the effect. I mean, so one subtle aspect of what I just presented is the fact that we have an opposite response to the wildfire variability in the northern hemisphere from 40 to 70 north and the Australian wildfires. One of them cools the climate system and one actually warmed the climate system, right? And so why is that? And I think the way that there are many ways that the aerosols can interact with clouds. They can thin the cloud field or they can brighten the clouds. And there are probably many more ways that they can interact. And so, trying to work through and then evaluate which is right, whether either is right with observations is work that we're doing. But certainly the latitude is part of the effect and cryospheric feedbacks are part of the effect.
We should probably move on.
Okay, so I'll talk about future projections of wildfire under different scenarios in CESM2. Next slide, please. So we looked at future projections under 7 scenarios from the year 2015 to the year 2100, and namely 5 SSP scenarios and 2 geoengineering scenarios. And these SSP scenarios range from the sustainable development scenario, which is SSP1 2.6, to the unmitigated baseline scenario, and which is SSP5 8.5. And the SSP5 3.4 OS is an overshoot scenario. It follows SSP5 8.5 through 2040. And then negative emissions is undertaken to rapidly reduce the emissions to 0 by about 2070. And the 2 geoengineering scenarios are both based on the SSP5 8.5 scenario, but they modify the climate system through adding the stratospheric sulfate aerosols or the solar irradiance reduction. And next slide, please. This slide shows the time series of global total burn area under those 7 scenarios. And the global total wildfire burn area is projected to decrease under the geoengineering and overshoot scenarios, but increase under all the other scenarios. And the largest increase in the global burn area is found under the SSP5 8.5 scenario, which is around 20%. And the largest decrease is found in the G6 sulfur scenario, which is around -11%. And next slide, please. This slide shows the zonal change of burn area in the period of 2091 to 2100 relative to the period of 2021 to 2030. And as we can see in that circle, the 40° north to 70° north latitude is the only latitude band in which the burn area consistently increases under all the scenarios, and even the geoengineering scenarios. And if you go to next slide, if we look at the regions, the strongest relative increase is found over the boreal North America. Under the SSP5 8.5 and SSP3 7.0 scenarios, the burn area over boreal North America will be about 3 times higher by the end of the century compared to the period of 2021 to 2030. And over the temperate North America, SSP3 7.0 leads to the strongest increase in the by the end of the century, which is about 100% increase, and followed by SSP5 8.5 scenario, which is 50%. And next slide, please. This figure shows the correlations of burn area with the driving factors over both boreal North America and the temperate North America. As we can see, relative humidity and soil moisture are the most important driving factors for the trend, which is consistent with previous studies. And it is also worth pointing out that under different scenarios, the impact of these driving factors can be different. And that's all. Thank you.
So we have a couple minutes for questions for Wenfu. It looks like there's one in the chat. Wenfu, do you want to answer Claudia's question? Who asked, did you investigate why the burnt area behaves as it does? What are the regional and global drivers and temperature preset, and in particular solar engineering? How is it both drying and cooling effect?
I'll type the answer in the chat.
Are you going to type it in the chat? Okay.
Yeah.
Alan also had a question in the chat that I might go ahead and answer. The question is, are fires and their smoke chemistry connected to climate? And at least the chemistry is not.
Emissions aren't.
Yeah, the emissions are not.
Yeah, so this is not an interactive fire run. What it is really just looking at the area burned, which really nicely leads to my talk, I guess, because we don't have at the moment model simulation that are fully coupled with the climate and run interactively. And that's really because we haven't really managed to produce a model version that realistically reproduces the historical trend of temperatures. So I guess I go into it when we go to the next talk.
Can I just clarify too that the carbon emissions are accounted for? So the carbon consequences on land are part of the land carbon cycle. And if we were doing a fully coupled BGC simulation, that would go into the atmosphere as CO, some of it would go in the atmosphere as CO2 and contribute to the overall CO2 budget.
Right. Should I go ahead with the next talk or?
Yes. Will, are you able to keep time still?
Yep. I'll reset the timer. Go ahead.
Okay, yeah, so this is really about the interactive fire emissions in CESM, and really it's motivated by the talks we had before, that many of the simulations we are doing are really with prescribed with prescribed emissions, for example, from CMIP6, the biomass burning. But it is really important to have the interactive fire emissions to get the right variability, to have the connection to the meteorology, because prescribed fire emissions are not responding to any of those climate situations. However, we do have, and that's what Wenfu's study is about, really the land model is describing all this area burned. So we have the information. And what we already have also is the coupling to the atmosphere. We have the capability to couple, and we have done previous model simulations where actually those fire emissions are getting into the atmosphere. We can look at air pollution, but we have not done any climate runs. And that's the point, is that so far when we did run a climate run, the model would not give the right temperature or historical distribution. It was even cooling. And Wenfu, actually, who just spoke, had done a lot of work on it before and identified some reasons for problems. And one thing is here, for example, when you look on the left plot, you see that in gray, this is the CMIP6 fire emissions, the fire carbon emissions. And what we can see is that it has a trend which is going from 2 to almost 3, and then going down and then up again. And usually fire emissions or area burned is evaluated, as we have seen, through the present day period where we have observations. But it hasn't been much evaluated in the past. Besides, there were now some recent studies like Hamilton et al. 2018 showing that we actually probably assuming way too low fire emissions during pre-industrial control. And so what we have done is we took the CMIP5 model, the CMIP6 model, the basic CSM 2.2 setup, and started from the pre-industrial simulations in 1850 and ran a historical simulation. But what happens was that we saw a sudden increase in the fire carbon emissions, as you can see in that plot. And then it would kind of stay the same and then go a little bit down. But the problem is in our pre-industrial control simulations, we are running without the land use. And so there's an accumulation of unburned carbon. And once we start then the fires, and in the historical simulation, we get the sudden increase of carbon emissions. And obviously, if you go to the next slide, that's impacting the climate. And you see on the right that the temperature would suddenly drop. And then while the model then itself would show a very similar trend, this kind of situation was something obviously we cannot keep. And so in the next slide, we had put now some effort together with some people like Dave and John, Marika Holland, and others to really set up a new pre-industrial control simulation. If you go to the next slide, please. Yeah, so that's a new CSM2 setup. Instead of starting from the pre-industrial control in 1850 and run it without the land use, we actually start in 1750 and run with interactive land. And in order to kind of spin up the model as a pre-industrial control, but have the land evolving so we can get the interactive fire emissions at a steady state, as you can see on the left top plot there. And so we also noticed, though, that after we first started, there were some imbalances of the model. We had a new setup. We have the latest land version. We used updated wet scavenging, and we were a bit out of balance. We were positive in the top of the atmosphere imbalance. So we also added some ocean emissions to this, which changed the balance. And then we performed several rounds of tuning, which finally got us to what you're seeing here, which is a pre-industrial control run with interactive land. So only the land is evolving from 1750, but the whole rest of the climate model is an 1850 control simulation. And in that way, now you see that besides having the higher carbon emissions, what we want, we do have about reasonable surface temperature. And then we were a bit concerned about the sea ice as well, which is a little bit low still. Nevertheless, since we are expecting that the trend may be different in the fire emissions in the historical run, we decided to start a historical simulation. And so in the next slide, this is, if you go to the next slide, please, you see just the start of the simulation. So this is the last slide, and it really is just started. I didn't have much time. There was some other mistake in the run, so I had to run over. But nevertheless, what we are seeing is so far that you do have higher carbon emissions, while the temperature and the sea ice is looking so far reasonable. So let's, we will go from here. We continue this run, and hopefully we can produce a simulation that eventually can be run fully coupled. Thanks.
Thanks, Simone. We've got just about a minute if anyone has a question for Simone.
Well, the other thing we are planning is, of course, then run in the future and identify variability between a model run that is interactive fires and non-interactive fires. So there are many things that can be done, but this is really just the homework first to be done before we can do this. Yeah.
And is there enough compute time to do a small ensemble here?
I think we have this community computer time project, you know, some computer time with our community project that includes also other model simulations, but this is one that we can actually do some of the historical simulations and do some ensemble members.
Okay, cool. All right, we can go ahead and move on then to Louisa.
Okay, so I'm going to talk more about the atmospheric composition impacts of fires. The next slide. There's already been a lot of motivation for the importance of fires, but I'm going to sort of outline some of the big uncertainties related to the emissions, the chemistry, and the transport of the plumes. So 80 to 90% of the emissions into the atmosphere are CO2, and a fraction, and then of that non-CO2 portion, which seems like relatively small, are CO and both volatile organic compounds and primary particles, but they really play a very important part in determining the atmospheric composition impact of fires on air quality pollutants such as PM 2.5, which includes secondary aerosols, and ozone, which depends on the chemistry. So as you can see, for example, on the September 4th, the fires in the western US emitted smoke that made it all the way across the country, and the air quality index was affected throughout the country, even particularly affecting Denver on this particular day. Next slide. So I've mostly been working with offline emissions inventories, which have different sorts of uncertainties. Some ways they're simpler than what's calculated on the land, but they also have other inherent uncertainties. So they're based on the actual detection on the location of the fire from satellite, from MODIS and VIIRS, as shown on the right here. And then the emissions are calculated based on the area burned, which has to be estimated, the biomass density and the fraction of the biomass that's actually consumed, and then the emission factor that tells you how much of any given compound was emitted per amount of fuel consumed. So for offline emissions inventories, there's the uncertainty of actually detecting the fire and getting a fire count for the fires, and then matching that up with a vegetation map to determine the type of fuel burned and estimating how much was consumed. And then the emission factors also have a lot of uncertainty, and there's not a lot of data covering all the different types of fuels that might be burned and how much they might emit. So next slide. So then once we get some amount of stuff into the atmosphere, there are additional uncertainties related to the chemistry and how the composition changes downwind. So the uncertainty in just the emission factors of things like NO and VOCs will result in uncertainty in the ozone and secondary aerosols that are produced. And there's also uncertainty in the representation of all the chemistry in the model. We have to simplify the amount of chemistry we have in the model. And so there are many more VOCs that are observed in fire plumes that are rarely included in 3D chemical schemes. And then, of course, the model resolution has a big impact, both horizontal and vertical, on the chemical regimes. So this plot shows the observed budget of nitrogen species in fire plumes during the WECAN experiment in 2018, and how it changes downwind. So it's including both chemical processing and dilution of the plume. And so you can see, like in the light blue, a secondary product of PAN increases as you go downwind of the plume, but the primary NO and NO2 in green decrease. Next slide. And so then, of course, transport is a big issue, whether there's plume rise, how high are the emissions actually injected, what happens in the boundary layer for the mixing, detrainment from the mixing from the boundary layer, or entrainment of remote smoke back into the boundary layer. And then, of course, getting the long range transport, because we know smoke can travel across continents and around the hemispheres. And finally, last slide. We've started doing some work on using the regionally refined version of CAM-CHEM with 14-kilometer resolution over the US, analyzing the two recent aircraft campaigns focused on fires, WECAN and FireX. And so that's just an example of the output for one day with the CONUS grid. And Wenfu's made a nice plot showing the CO concentration at the surface for each grid box for a particular fire that the DC-8 sampled, and showing the flight tracks. And this really indicates that perhaps this resolution is sufficient for analyzing these campaigns and critically evaluating the model. And so hopefully we can discuss some of these all in the later discussion.
Thanks, Lisa. We've got about a minute for questions here too. Dave, go ahead.
So have you tried to look at like an even lower resolution version of the model, see how it's, because as we go into this fully coupled 1 degree version of the model, I guess there's a question about, are those emissions being processed and transported downwind in anything like a realistic manner, or is it become completely unrealistic in a 1 degree resolution?
Yeah, we've done lots of runs at 1 degree, and it depends on the scale that you're looking at. So I think, away from the fires, often the errors in chemical regimes average out. But if we want to really evaluate the emissions, we want something at a finer scale, and maybe even finer than 14 kilometers. So for huge fires like the Australia fires, probably 1 degree is fine, where you have fires over many grid cells, even at that scale. For the FireX campaign, there were very isolated fires, and so we're trying to do some very detailed comparisons, and it's more difficult at coarser resolution.
Great, thanks.
Yeah, thank you, everybody. It's a really nice, motivating talks for our discussion. And so now we're going to switch over, and we'll have a short poster presentation, like sort of a come see my poster. But please do come to the poster session. We have some great posters. And so Douglas, you'll be up first.
These are 3 minutes, right, Jackie?
Yes. So
Right.
3 minutes, then some time for questions. And then we will take a short break before the discussion.
Okay.
Douglas?
Great, thanks. So I'd just like to start by thanking my co-authors and the organizers for allowing me to come and talk today. And also thanks to Simone for kind of highlighting some of what I want to just point out in this short talk here. So aerosols from fires can impact the climate and earth system in many ways. My poster will be focusing on two particular aspects: the aerosol radiative forcing and also the role of fires in providing nutrients to remote ecosystems. And for this lightning talk here, though, I really just want to mainly focus on the uncertainty in the trend and changing magnitude in fire forcing over the historical period. And if we look at the numbers at the bottom of the plot here, we've got four different estimates of pre-industrial fire emissions, and also the present day carbonaceous aerosol emissions for comparison. Though I can't go into all of the details in the differences between these four different estimates, they can broadly be summarized that the two fire models on the left-hand side with the higher fire emission estimates specifically represent land fragmentation and the impacts that has on fire suppression. So things like increasing agricultural or pastoral land use. Whereas the two estimates on the right-hand side, the lower estimates, have either minimal representations of how land use, land cover change impacts fire emissions, or in the case of Aerocom, none at all. This produces a wide range, as we can see here, in the aerosol emissions. But when we investigate paleo environmental archives of the change in fire emissions, for example, things like ice cores or the charcoal record or dendrochronology for fire ring scars, they all generally seem to point to higher fire emissions in the pre-industrial as compared to the present day. So how that uncertainty in those different fire emission estimates in the pre-industrial propagates into the range of uncertainty in the pre-industrial to present day aerosol radiative forcing is what's shown on the plot on the top. With a higher fire emission in the pre-industrial, we end up with a smaller difference in the aerosol burden between the pre-industrial and present day, and that diminishes the aerosol radiative forcing over the same period, and it was a small aerosol radiative forcing. In comparison with a lower aerosol emission in pre-industrial, a more pristine aerosol state has been assumed, you'll end up with a higher aerosol radiative forcing over that period. We've run this experiment twice now, most recently on the orange dots, that was with the CESM2. And what we can see here is in comparison to our previous experiment in 2018, the CESM2 has a higher sensitivity to this change in aerosol in the pre-industrial than the UK model that we used before. For comparison, in the gray region, what I'm showing there is the full range across the aerosol forcing from AR5 from all the models that partook in the CMIP5. And we can see that that actually mirrors the range that we're predicting here from just the uncertainty in pre-industrial fire emissions. So that is suggesting that fires could represent the largest uncertainty in predicting human climate change, and really highlight how fires are a core component of the coupled Earth climate system. And if you'd just like to go on, yeah, lovely, thanks. And also within the poster, I want to just highlight that we've been working on developing a module for MAM4, which can predict both aerosol, iron and phosphorus, which further links the land, atmosphere and ocean components. And if you're interested in knowing a little bit more about that and how fires impact marine ecosystems, then I welcome you to come along and have a chat with me later, or about the aerosol radiative forcing. Thanks.
Thanks, Douglas. Sorry, I wasn't sure if I was supposed to advance, so.
That's fine.
Dave?
So this MAM4 work, is this, I know that Simone has been talking about some new work with the aerosols. Is this related at all, Simone, to what's going into the simulations we have now? I mean, it's unrelated.
The iron and phosphorus on the right-hand side, or the aerosol radiative forcing on the left-hand side?
On the right-hand side, the work with MAM.
Yeah,
no, this is separate.
Okay.
Yeah, this is separate. Although it's available on a branch in CAM6. If anybody is interested in running iron within the atmosphere, then we can help support that. Happy to collaborate with anyone, but it's not currently in the project line for CAM6 as far as I'm aware.
Okay, next up we have Danielle.
Hi.
And
You
Danielle.
can start on the. Oh,
Okay.
sorry. So you can start on the next slide.
Okay, go ahead.
So this work is motivated by recent debris flows and flash floods that have occurred after fires here in Southern California and also across the Western US. And so next slide, please. And so using the CESM large ensemble, I'm a little behind you guys. I'm still using CESM 1. We see that both the frequency of extreme fire weather events and the frequency of extreme rainfall events are increasing in future years. This is compared to a historic period. And this is under RCP 8.5. So next slide, please. So we wanted to use the CESM large ensemble to see if we can capture the changes in these rare events and kind of their timing and see if they're occurring kind of consequently to create conditions that could lead to debris flows and flash floods. And what we find is that indeed they can. These increases in the frequency lead to a greater likelihood of extreme rainfall events occurring within 1 year or less of an extreme weather event over all of the Western US. Next slide, please. And we see that this change, can you advance one more? I think I have an animation in there. Yeah, so this change in the likelihood is partly driven by an expansion and amplification of wet seasons and fire seasons. So this is kind of the seasonal changes in California. And we see that there's kind of this both amplification and expansion of both the fire season and the wet seasons in the future. And I think I have one more slide. That's an advertisement. Yeah. So come to my poster to see more details on methods and data, more seasonal and regional variations in these types of compounding extremes, and much more. So thanks for having me here. It's been a great session so far.
Got a minute or two for questions for Danielle?
I have a methods question to see if I understand. So that you looked for an extreme fire weather occurrence, I guess, in each month, and then for a subsequent extreme precipitation event. Is that how you did it? It was within within X years, within.
Yeah. So we look at both within 1 year, 2 years, 5 years, and then we also look at like sub-annual to kind of capture these more type of extreme events, extreme conditions that could more likely lead to things like debris flow and flash floods. So that's kind of
So that's really cool. So I guess so after a fire, even a not that extreme event, precipitation event can lead to a debris flow and floods and
so that's we actually only use the 99.9th percentile of rainfall because we want, so there's this kind of issue with the CESM large ensemble simulations where the smallest kind of temporal scale we have is 6 hourly. But to really capture things like debris flows and flash floods, you need more of a sub-hourly estimate of rainfall intensity. So we wanted to capture this like top 0.1% of rainfall events to try to at least get at these really high sub-hourly rates, or high sub-hourly rates, yeah. But I guess you were asking kind of like, did I look at lower thresholds that maybe could lead to debris flows and flash floods? I think I used like the 95th percentile at one point, but we kind of went with this really high threshold to really capture these really extreme events.
Okay, thank you to all of the speakers, and thank you to everyone who's here for the session. Let's take a short break and come back at 5 minutes past the hour to have a discussion. Thank you. Okay. Welcome back. I'm going to put up a slide with some initial discussion questions or discussion points. Too many slides. But in the meantime, if anyone wants to, while I'm looking for this discussion point slide, if anyone wants to start us off, that would be, here we go. So we really just wanted to open this up to the community so that we could come together and talk about how do we handle fire in a coupled fashion? What are our priorities and what are the obvious challenges? And so I know that there are a lot of communities that are interested in fire. It affects a lot of different parts of the system. And so that's part of the reason why we wanted to come together as a group to talk about this. Are there opportunities that we have to look at things together? Is there something that we're missing? You know, we can start at the top of the list. We can start with my favorite topics. It's really open. But one of the things that came up in the chat after the talks was the connection of lightning. And so at the moment, lightning is considered as a part of a static data set, but a data set that varies spatially as well as temporally. But there's definitely an opportunity to include lightning as connected to CAM. Go ahead, Peter.
It's a great discussion. I was wondering, are we ever thinking about using the fire model in an operational sense, like, you know, like a wildfire model, like at really high resolutions, or is this always going to be more like statistical type model to understand the carbon cycle, ecosystem impacts, that sort of thing?
And so your question is like an operational scale model for like firefighters on the ground,
right.
communities. Yeah. I think it's a good point. The opportunity is certainly there to connect with folks at RAL who are doing this sort of operational scale fire forecasting. The Lee fire model and Spitfire are both more at the fire regime scale. And so it's a larger spatial scale as well as a longer time scale, but something that you can get from these models connecting to an operational model is a description of how the fuels change in time. And so with a lot of these operational models, they look at a fire event on the order of days. And so the fuels are more static and they're consumed, but they don't necessarily change in space and time. And so the connection between these types of models to inform the fuel maps would be an opportunity. Dave.
I wonder if Rebecca wants to follow up because she might have a comment on that, if that's what her point is. I see her hands raised, and I was going to change topics a little bit. So.
I was going to change topics a little bit as well, but it's semi-related. I was just going to make the comment that it might be interesting to be able to use fire counts from satellites to put into the model to then use those to drive everything else interactively. And then you can test real fires and the result from real fires in the interactive model, potentially.
Yeah, that would be a really nice feature. And that would not be that hard to do.
Could I jump in? This is Sam Levis. Let me just turn on my video as well. In response to what Rebecca just said, some of the work that I did with Lara a year and a half ago or so was to expand that capability of ignitions to beyond just lightning, actually, even observed ignitions, which may include ignitions because of lightning, but also ignitions because of other human activity. So, that capability, I believe, is now within the main trunk of the CTSM. And so then the data sets can be swapped. It could be a lightning data set or some more generic ignitions data set.
And so, Sam, is that operational with both the Lee fire model as well as FATES? I know that it was tested with FATES.
Right, it was tested with FATES, but the software engineers, in particular Eric, helped me out to make it work. I believe the way that it works now, it could be for either. And correct me if I'm wrong, Eric, but I think that's what we did, right?
Yeah, just to clarify, so what can be done is that the lightning and the population density can be used by either. Sorry, I have a little dog barking. But the lightning ignition can only be used by FATES.
And by that, you mean the like a user prescribed ignitions data set?
Right, exactly. That can only be used by FATES. But both FATES and Lee can use the same population density and lightning data sets.
FATES has the ability in the parameter file you set which ignition data set you want to use. So it's could be lightning, it could be observed ignitions, or it could be some other anthropogenic type. But we still haven't implemented sort of more anthropogenic ignitions in FATES yet. But it's a selection.
Dave Bailey.
Oh, thanks. So I wanted to follow up on Rebecca's point about the satellite validation, because especially in the high latitudes, I was kind of nervous about the tuning that we did for the pre-industrial run, and I don't really have a good sense of how realistic are the fires that you're getting in the pre-industrial. And so once it's through the 20th century, it'll be really interesting to see how it compares, present day and so forth. Because those sea ice albedo values that Simone presented are definitely at the high end of what I feel comfortable with.
Okay, Douglas, do you want to follow on that?
Yeah, maybe just to advocate that when we're looking at these kind of fires in the past, it's maybe not a good idea to overly constrain with present day satellite information, but rather to use the information that we understand about the past. Otherwise, it's taking the assumption that the way that fires are impacting various different climate regimes, or being impacted by climate regimes, or impacted by human activity in the present day, that is exactly the same in the past, and it's most likely quite different. So there's a wealth of paleoproxy data kind of sitting around. Some of it has been analyzed. There's been a brand new paper out just in the last couple of weeks in Science, for example, from the Harvard group, where they've been looking at black carbon in the ice cores in the Antarctica. I looked at some of the black carbon in the ice cores in the Northern Hemisphere. And I think that there is more that we can do there to constrain what's happening in the past. But I would, like I say, advocate not taking what we know from the satellite era and then trying to apply that to 270 years ago.
Great point. I'm going to put a new data set that's coming out with a paleo history of North America. But then, Dave, Dave Lawrence.
Yeah. So that's a good point. I think this whole validation thing is quite challenging. I guess I want to step back and just, I'm not sure how much it's clear that this new simulation that we're doing with interactive fire, as far as I'm aware, might be unprecedented in terms of a persistent model. Someone can correct me if I'm wrong, but there'd be very few groups around the world who could even try to do this. And so we kind of have to expect that things are going to kind of go wrong when you try to do something brand new. And so we're going to see what those are over the next several months, I think, about what goes wrong. But one thing that occurs to me is that one possibility is that, one possibility is that the fire model as it is now is going to, since it's more like a statistical fire model. And I was asking Fong this before the meeting, if she'd ever looked just at a time series on a time step level what the fire output looks like, because I have no idea what it looks like. I've only seen these long-term averages. But my guess is it's just kind of like fire almost every day in the Western US, but just a small fire. That could be what it looks like, which is maybe not that unrealistic these days. But so one question I'm gonna be looking for as we go through these runs is, like, if we have a bunch of small fires dribbling out aerosols, will we get a climate effect that's realistic rather than big fires which are generating a lot of aerosols over a short period of time for a few months in summer? And is there a way for us to distinguish between those two? And if we do find that's the case, then what would we need to do to be able to represent it more realistically in the future?
Yeah, that's a really good point. Will, do you want to follow on that?
Yeah, I guess I was curious, since you're building on Dave's comment that this is maybe the first time this has really been done in a coupled sense, if there were contributions from the paleo group to this kind of fire working group session, kind of speaking to Douglas's point about using that record in addition to the satellite record. And then the other question I had, I guess this is more for Louisa, but in the chemistry, is there any effort to try to keep the vegetation that's generating the aerosols consistent with the vegetation that CLM thinks is there? It's probably easier for the big leaf model than it is for FATES. But for these runs where we're prescribing vegetation, are you guys using the same vegetation that the land thinks is there?
I'm not entirely sure what you're asking, but when I do runs like with the thin emissions inventory or QFED or whatever, they use their own vegetation map. Okay. We could certainly modify thin to read a CLM vegetation map, but it's thin currently uses a MODIS file. Okay. Uses the current MODIS observations of vegetation.
They're probably similar, but not the same.
Yeah. That would be an interesting experiment to compare.
Simone?
Yeah, I was going to comment first on the chemistry too. I mean, if you run interactive, of course we use the same land types, right? That wasn't your question, or was it? The interactive fire model and the emissions are obviously consistent with the land.
Yeah, I guess I didn't know if the interactive fire model that you're running now had the chemistry turned on, or if the Musica.
Yeah, if it has the chemistry turned on, it will take the emission directly from what the land is producing.
Okay.
So there is no other land map that the chemistry would use. I think that was also the question, or maybe that was one of the thoughts. Yeah, so that's consistent if you run interactively. The point that Dave made in regard to the variability, I mean, that's really what John's study showed. And maybe John, you wanted to comment on that, right? If you have the large variability, you suddenly get a very different climate forcing different aerosols. And so that's probably something we can learn. And the last point I wanted to really make is that the problem is with these fire models are compared, as we already said, to the satellite era. And so the how much we have really in present day is how we tune those models, which doesn't mean that it's the correct way. And that's a really good point, what Douglas made. So how do we actually tune the model? How do we use the black carbon from the sea ice to core, to compare to how much black carbon was in the atmosphere. I think that would be an interesting thing to think about for pre-industrial times.
Yeah, good points. John, do you want to follow up?
Actually, I had a question, and that is from somebody who's not a land modeler and is new to this. How will we know if the model is wrong? So, black carbon burdens and aerosol in ice cores will tell you some aspects, but we really want to know more than just the mean deposition. We want to know the full PDF of fires, and those will have a climate effect. And so what are the ways that we'll be able to tell whether our simulation is reasonable or not? I mean, judging from the CMIP prescribed emissions, it's clear that there's a lot we don't know. And at least in a global sense, how will we know if our simulation is reasonable?
I can try to answer that a little bit. I think it's hard, and maybe Jackie has a better sense. But what Fong has done in the past is do things like compare to the GFED satellite for fire counts or fire or burned area, and so that's one measure, but that's pretty gross. And you can also look at interannual variability in burned area and fire count. And then I'm not sure what status she uses, but total fire carbon emissions. There are estimates of that at present day. Again, so we have some validation that on both of those counts or both of those statistics, we are in the very broad ballpark.
Right. Yeah. No. Back of my mind was the caution that Doug just made that we shouldn't be using the satellite era to extrapolate back in time on what's reasonable, right? So that throws both of those, sources out the window. And so, what's left? You can look at the temperature record or other, very indirect indicators, but that's not ideal either. So,
I think so. Adriana Foster put something in the comment to look at above and below ground combustion, post-fire dynamics, and fire intensity. And then I want to also loop in the connection to the chemistry. And so these emission factors, a lot of them are biome level emissions factors. And so if we can get more data on emissions connected with, genus or more specific vegetation types, that would allow us to connect a specific type of vegetation burning to types of emissions. But you're right, it's going to be complicated for the past. And so one of the ways that you can get at that is to try to capture the vegetation types. And so this would be more for a dynamic model rather than prescribed vegetation. But it's absolutely a challenge. Wenfu, you want to jump in?
Yeah, I just want to follow up Dave's question before. So is it the same when you have a big, large fire or a bunch of small fires emitting the same amount of aerosols to the atmosphere? I guess the question is also, besides the total amount of aerosols get into the atmosphere, the location where they get into is also important. Like when you have many small fires, their emissions will be most likely within the boundary layer. But if you have a huge, large fires, their emissions will get into the free troposphere and even the stratosphere, so that will have different impact. Even if they have the same total amount of emissions. I guess that's so those big fires, although not as common as small fires that happen every day, they may have even larger impact.
I think. Yeah. Can I just it sounds like I have more, but let me just respond to that. Is one, I think then, as far as I'm aware, all fires will, for a particular plant type, it'll always put the aerosols at the same injection height. Like we don't have any like fire intensity relationship. Can someone correct me if I'm wrong, Simone, or I saw Maria was on. So that's something we could try to fix in a future version of the model to have connect that to fire intensity unless it's already there. So
Yeah, it's not there.
Yeah.
The only thing is that it's PFT dependent. So if you have a different larger trees, then you may get more, higher plume height. So that could be something that is already there. That's the dependency.
And I have a question for Jackie. You plan to implement the FATES file to CLM. Am I understand correctly?
Yes, I'm implementing it now, and I've been testing it. And then, but we have parallel efforts. And so I've been testing it in the tropics, and then we have folks testing it in California, and I'm testing it in Boreal Canada. And so yes.
So is it a column model, like individual grids? Do they communicate model?
There is no communication across grids. So propagation does not happen.
Oh, I have a question about the resolution. For example, if in the future the resolution gets higher, how do you deal with the column not communicating with other column?
In terms of fire propagation?
Yeah.
There's a bit of this discussion kind of going on in the chat also, and I think Eric maybe said it most succinctly that CTSM isn't well designed to handle things like propagation of fire from grid cell to grid cell. So adding that ability is a big lift. So as we move to higher res, if you do want fires to jump across grid cell lines, that's going to be something that changes how we run the model.
Yeah, like when the model resolution is gets really high, like for example, the current regional refinery we are using 14 kilometer. If we want to couple that to the land, and some fires maybe have larger, fires with size larger than 14 kilometer could occur in reality.
Yes, yeah, you're absolutely right. And so it's going to depend on the area that you're simulating. And so if you have fires that are larger than your grid cell, it's going to be problematic for your simulations. And so 14 kilometers is quite big. And so I think, Adriana, do they have fires bigger than 14 kilometers up in the Boreal? Excuse me.
I'm trying to find an estimate for the average fire size, but they can be quite large. Yeah.
But then the other point with this is even if you have grid cells that have similar fuels, if you have similar conditions, you will get ignition on co-located grid cells. And so it's not propagation. And so we do need, excuse me, we need to look at this issue of propagation. Absolutely. And so it depends very much on the resolution that you're simulating at. And so no, FATES is not doing propagation at this point. As Eric said, CTSM isn't set up to do that yet.
But yeah, I brought up propagation because Peter had asked about operational use. And I think, the firefighters, they really need it to be spatially propagating because they need to know, where are we going to go tomorrow? Or where do we need to put in the next hour, where do we need to go? And so I guess that's just my comment, was that I don't know if Spitfire in FATES, it would be good for that operational use, but I think it is useful for managing forest stands for fire. So we can say, given this type of forest, it's very flammable or something, or it will be very flammable in 20 years or something like that. Sorry, that was the side, but yeah.
I'd just say that, for fire, like predicting fire evolution from a specific fire for firefighting purposes, I mean, NCAR and RAL already has a system. And if this group was going to become involved in that at all, I think it would be through using CTSM column model to improve the quality of the soil moisture and fuel loads rather than the fire model, because they have a detailed fire model that's accounting for all the wind and the how it races up a slope and things like that. But I don't think there's any current plans to try to merge efforts there. As far as I'm aware, we're pretty divergent in that. But we'll see as we are moving more and more towards weather with weather applications with CTSM. That door might start opening up, but probably not the fire model itself.
And so in the chat, Laura also brought up the point of multi-day burning. And so within a lot of areas globally, multi-day burning is a consistent behavior. Within the Spitfire model, there is a limit on the length of time fires can burn. I don't recall if that's true with the Lee fire model, if there is multi-day burning. And so we've talked about some solutions for that, but it's something to keep in mind as you're looking at these models, because it's definitely unrealistic to have a cap on burning.
The Lee model is a 1-day fire. All fires are 1 day.
Yeah, and I think there's a connection to the forecasting, right? So far, how do you simulate 10 days ahead if you want to do a forecast? If the fire is continuously burning right now, what we do is we just continue our fire emissions as they are. When we stop, at the day of present day, we just let the fire burn. But how can this be integrated better, that you can do better forecasts?
Well, and I think it depends on what timescale you're talking about with forecasting, because like operational fire models are at the level of the fire event, and that's like well outside the abilities for something like Spitfire. But if you're talking about projections where you're going to look at management for your community and look at how am I going to handle fires inside the wildland urban interface, having a cross-scale integration of these fine-scale operational models, as well as something coarse scale, to give you an idea of the resilience of the system, or the projections on how things might happen. I think that can make sense. But when I think of forecast, I think of like firefighters on the ground. So which scale were you referring to, Simone?
Oh, I just was thinking about a short time scale of 10 days or something like that.
And for air quality, I presume is what you were thinking of.
Yeah,
so
yeah.
Not where is the fire going to go, but what is the air quality impact?
Well, you also want to know where the fire goes for the air quality impact, right? I mean, it's both relevant, I would think.
Right, if we could do something on that sort of scale.
Yeah, I think with these models, there's a lot of uncertainty at the daily scale. But I don't know, maybe Dave, you feel differently.
Oh.
Yeah. Adriana, please jump in.
I guess this is shifting gears a little bit to how we can validate like fire intensity, because that's one of the main things that we calculate in Spitfire model from Rothermel. And I'm wondering, that MODIS has the fire radiative power, but I have had a lot of trouble sort of getting the fire radiative power to be, I don't know, not like totally crazy itself. And I don't know if anyone else has experience with looking at that, or if people have other ideas for how we can validate fire intensity, or if we even need to.
Douglas?
So I don't know how you could validate it, but for the last point about whether you need to, the intensity of the fire will predict the ratio of black carbon to organic carbon, which is released. So in terms of the climate response, with black carbon being warming and organic carbon generally being scattering and cooling, it can be pretty important. So I think yes, but I don't know how to do it, but just to say, from an atmospheric person's point of view, it seems like it potentially could be important to get that intensity right, particularly if it's changing over time.
Yeah, I agree. It's important. Lara, go ahead.
I was just thinking that's really interesting. And I guess I was wondering two things. One is how well known those ratios are as a function of intensity. And then also whether they can be observed more easily than fire radiative power, or if they're similarly difficult, whether it's similarly difficult to observe that ratio of black carbon to organic carbon.
Yeah, I don't know about at the global scale, but certainly when they do prescribed burns, you can see it quite clearly. You know, at the fire front, it's all black smoke, you know, that's kind of coming out where it's hot, so the very high black carbon. And then in the smoldering phase, which lasts for a long time afterwards, you know, it's much more organic, that white smoke. But at the moment, the way that most models do it is they just take, you know, one emission factor for one particular fire, regardless of its, you know, the power or the intensity of that fire. So, you know, the emission factors themselves would likely need to be retuned, I guess, or rethought about how they interact in terms of not just the PFT, but how complete that combustion was, I guess, of the PFT.
So from a climate response point of view, getting that vertical structure of aerosols is critical. And I would think that, you know, what clouds it's actually interacting with, whether you're interacting with the low cloud field or the high cloud field or getting into the stratosphere. It sounds to me like the partitioning you're talking about actually really affects the plume itself.
John, thank you for that point. And Dave, do you want to make a comment? But then I would like to shift to talk about, you know, characterization of smoke and plume dynamics, if we can. Dave.
Well, that's actually maybe where my question is leading. I'm wondering if, you know, we're doing these simulations as a new baseline, whatever simulation of climate change with interactive fire, and whether we need to design some sensitivity experiments around this that would probe some of these questions about, you know, even if we don't know the answers, you know, we could obviously make decisions about injection height. We could make more simple parameterization of injection height based on a, you know, simple fire risk factor, or you could do something simple about black carbon versus brown carbon, you know, and just see what the climate response is and get a sense of, you know, which one of these things is the most important thing to work on.
Well, and then there's chemistry, just to add in, because right now these simulations are not with chemistry, but you do get different answers, as we have seen from the CI's study from Alice Dubuvier earlier. If you run with interactive chemistry, there's other effects that, who knows if that matters, but we want to try that.
And so Wenfu, I know that we had talked previously that you're implementing a plume model. Do you want to talk a little bit about that?
We just started a study trying to improve the representation of fires in the CAM. So we tested adding fire diurnal cycles and also adding plume rise, but those are offline. So what we did was we add those add a diurnal cycle and plume injection height to the offline emissions and put that as input, use that as input to the model to CAM. That's what we have done so far. We do find that adding diurnal cycle and plume rise preliminary results improve the model agreement with observations. Plume rise and the diurnal cycle of fire emissions should be considered together because they are also interact. And I have a presentation tomorrow if anyone is interested in the chemistry climate session in the morning.
Yeah, there are definitely, thanks for bringing that up, Wenfu. That sounds really good. There are definitely relevant fire talks happening in other sessions. And so one of the other things that came up in sort of thinking about this session was to think about how we can improve representation of fire suppression. And so I think consideration on fire management in general, so prescribed burning, thinning, as well as fire suppression, it needs to be a component of, development moving forward. And so, I talked about, we're thinking about that on the FATE side. And then Adriana said lower branch pruning. And so how can you modify your forest to adapt to these fire regimes? And so I don't know, Dave, if there's anyone thinking about specifics with the management side.
I know Fung is intending to work on it more, but I think she's not looking at it from the forest structure point of view. She's got this economic population trajectory kind of overarching perspective, which probably needs to factor in, right? It's the rich countries that can actually manage their forests or try to manage their forests. So I think with FATES is where that, it's going to be pretty interesting to try to merge that. But I do feel like that, it'd be good to start bringing in at least the FONG's inputs, to help drive, as a forcing factor in terms of determining where the forests are being managed, GDP or population or other socioeconomic factors.
Yes, yeah, we actually have an issue discussing how to implement anthropogenic impacts and suppression just based on Fong's work. And so just using the same methodology as a starting point, absolutely. But with FATES, a lot of the applications at this stage are regional. And so there is a lot of interest in targeted management that would be specific to an area like California. And so it's a specific approach. And so there's a balance of approaches within FATES. And then Donica points out in the chat that we need a better representation of agricultural fires. And I absolutely agree. One thing to note with agricultural fires is for the satellite record, satellites definitely have a blind spot in terms of detecting these fires. A lot of the areas, they know that the satellites are passing over and use these detection algorithms to capture fires. And so they do their burning at night. And so there are incidences of fires where they burn their crops, but you don't necessarily know about it. And so it's sort of a missed connection. And then Lara points out that fuel wood gathering is important. So yeah, and we're talking about this within FATES, but as I said, this is regional specific. Senlin, would you like to comment? You've been giving us a lot of information in the chat. Do you want to comment on wharf fire or some of the other things that you've brought up?
Yeah, sure. So earlier I put something in the chat regarding both the emissions and the plume rise. So some of the studies already used the quantitative connections or relationships between the BC versus OC emission ratios to the combustion efficiency. Some people use that in the global simulations of the fire-emitted aerosol effects. For the plume rise and injection height, if we are going to interactively connect that the plume rise process with the service fire processes, then we could probably adapt some of the existing parameterization to link the plume rise or injection height to the fire-induced heat flux and buoyancy. I know there are already some parameterizations used in Welfire for the interactive simulations. And the last comment or questions I put in the chat is that do we have the observed or sort of analysis fire data where the different fire types, for example, the natural versus anthropogenic, are separated? Otherwise, we could not constrain that. I know some of the fire data set like the NIFC, National Interagency Fire Center, or the MTBS, the monitoring trends in burn severity. Maybe some of these data sets have differentiation in different fire types. But I don't know if anyone knows any like comprehensive data set people already put together for us to validating or constrain the model fire input. Yeah, I mean the ignition source.
Sure. I'll give it a minute if anyone wants to step in and comment on that. I don't know, Laura, did you want to? Oh, she dropped away. The data sets that you highlighted, and then Danielle Tuma highlighted CAL FIRE. And so I know that there's been work done within California. And so you're going to be limited based on the regions for that separation of natural versus anthropogenic. There's also been some work in the North American boreal separating those. But it really does depend on where you're talking about. And so finding a global validation is going to be a challenge. Laura, did you want to comment on natural versus anthropogenic? It's possible she's not there.
Yeah, no, I'm here. Yeah,
Okay.
I was just chatting about something else in the chat. The FRAP, the CAL FIRE FRAP data set does do that separation, but like you just said, that's for California.
I guess I do wonder if someone's suggestions about WRF, like that's something that can come into CTSM. Some of that plume height and emission factors are already in, in a model. Can we bring those into CTSM?
Seems like it's worth some exploration. That there's the broader question about how long are we going to be maintaining WRF with this unification effort across NCAR. And so at some point, WRF is no longer going to be supported. It might be many years down the road, but if WRF fire is not supported anymore, they're going to have a replacement for it. Could be MPAS CTSM, right? Someday CTSM fire. So if it wouldn't hurt to start now to start bringing over capabilities.
Yeah. So I want to follow up with Dave's comments. So regarding that, I think there is also a potential issue when we look at the CTSM fire or FATES fire and the WRF fire, because the WRF fire model, as far as I know, it is more suitable for the fire event simulations where you have a very detailed fire spread and fire-related heat flux and the interactions with the weather. And for the CTSM fire or even the FATES fire, it is probably more based on the parameterizations suitable for climate simulations or like relevant scale studies. I'm not sure if I understand correctly, but if that is the case, when we apply these different models to the specific applications, we may need to keep in mind if that is a suitable tool to use, especially when we do the unifications, because some people raise the question that part of the parameterization used in the current CRM file is actually based on the statistic relationships, which is more in the climate sense instead of maybe a weather scale sense. So it's just a caution, I guess.
Yeah, absolutely. I didn't. Yeah, no, I think that these are very different beasts. And so this is maybe a different problem outside of the problem we're discussing here, which is more climate related. Which how is NCAR going to manage these different fire models going forward? It's a different question. Probably should leave that for another time.
Rebecca, go ahead.
Yeah, I just have a quick comment on the natural versus human fires. I would just have to find the reference, but Jennifer Balch recently published a paper looking at the whole of the US and lightning ignition versus human ignition and how humans expand the season of the fires. And so she used the US Forest Service Fire Program Analysis Fire Occurrence database, and that has information about how the fire started, as well as I think these are only relating to fires that I think needed to be suppressed. But so there is a data set for all of the US.
Yeah, thank you, Rebecca. And you're absolutely right. And I think Jennifer's work shows that more than 80% of the fires in the US are started by humans. So we only have a few more minutes before the end of the session. And then the poster session starts at 3:20. So there will be a break after our discussion. And then I do encourage folks to check out the poster sessions. You'll be able to visit individual posters and interact with the authors. And so in the chat, Adriana brought up the point of the interaction of fire with other disturbances. Adriana, do you want to expand on the importance of these interactions?
Sure. I mean, I guess we don't maybe know the importance of them yet. I think that most disturbances are predicted to increase in extent and severity in the area, like sort of expanding into new areas. And I'm just, I think that the potential for disturbances to interact is going to increase. And, I think there's been a lot of studies looking individually at that, and then studies saying like, oh, this is really important, we need to look at it. And I don't know if it's really been put into a model yet. And I think it's an important step forward. And I think if we can get the fuels and interactivity right for the fire, it will set the stage to then add in, like what insects or like thermokarst, and speaking from like a boreals perspective, but yeah.
Yeah, I agree. There are a lot of uncertainties and a lot of opportunities. And so improving our ability to capture how all of these pieces work together has the capacity to improve all of these fire models. There are, known uncertainties with emissions factors. And so capitalizing on the measurements from the campaigns, getting a better characterization of emissions where we can attach that to changing fuels on the ground would improve our emissions in that sense. Thinking about the Plume model and yeah, following up on all of these connections, I think will be important moving forward. And Senlin made a point in the chat about drought-induced vegetation, soil moisture. and fire ignitions. And so I brought it up in my talk briefly, but the importance of live fuels and the transitions of live fuels to becoming an important fuel source, I think is a critical thing as we move into this more drought-prone climate, especially here in the United States, but it's valid in other systems that have, a dominance of shrubs or grasses. Consideration of changes with your live fuel moisture is going to be an essential part. And then combustion and emissions for live versus dead fuels is highly variable. And so, Louisa, do you look at that specifically, like the variation in combustion based on like fuel moisture?
For example, Finn does not include that.
Okay.
No, that I don't really know any details about other inventories, but I think not in general.
Okay.
But that certainly, if there's satellite data, or if there's other information, that might be interesting to include.
Well, and I think this comes back to the scale of where the data is. And so if, a lot of this data is point measurements or a field campaign, and so it's not necessarily global, but how can we take those field campaigns or these site level measurements and use that to inform things in a mechanistic way so that we can handle it more at a larger scale? It's a challenge.
Yeah. Yeah, I think there could be a lot of benefit in using this FATES capability of, reading in existing fire counts, fire detections from satellite, and then using all of the information in the land model to calculate the emissions. I'd really like to pursue investigating that, using that, and then comparing directly to some field campaigns. I think that could be very beneficial to help understand all the driving variables and where some of the errors are.
Absolutely. Well, if I think the methods of how we're going to tackle this is really important, and we're just going to have to keep talking with one another and staying in touch on it. One of the other opportunities that I see with FATES and then with consideration for this interactive fire is the importance of the paleo world. And so looking at how things have transitioned over time. And so I know that I've talked in the past with the paleo community about just looking at dynamic vegetation and how fire has changed the distribution of vegetation. And so it would be, and I haven't thought about that, how you go from paleo to neo, like how you go from paleo to modern. I recognize that that's a big challenge. And so, but it would be good to explore that, especially with large scale fire histories coming on. Well, if no one else has comments, I want to thank all of our speakers, and I want to thank everyone for coming together and bringing your ideas and bringing your questions. We're definitely not going to solve this as a party of one. And so please do get in touch if you have further ideas or further opportunities that you want to bring to the group. And so please do come and visit the posters, and yeah, let me know if you have any follow-up points. I'll save the chat from the discussion. You can also save the chat by clicking on the little dots down there and save it for yourself. Thank you to everyone who put information and references into the chat, and for sharing your ideas. I appreciate it. And so hopefully I will see you all at the posters or at these other sessions. Thank you.
Thank you.
Thanks, Jackie.